Welcome to Mark's Tech Talk. In this video, I'll be discussing transformers. We'll start out with what exactly is a transformer. It's simply two inductors placed close together so that they are magnetically coupled to one another. We have symbols that look like this, and you can see the first inductor is physically placed next to another inductor, and sometimes they are wound around an iron core to better facilitate that coupling of the magnetic fields. So the first part of the transformer, the first inductor, creates the magnetic field, and the second one is inside that magnetic field, and that magnetic field is changing, so we actually induce a voltage in the second coil. So the part that's connected to a source that creates the magnetic field, that's called the primary. And the part that's connected to the load is referred to as the secondary of the transformer. Since we usually have signal flow from left to right in the schematic, in most cases the left-hand portion of the transformer will be the primary and the right-hand portion will be the secondary. Okay, so we're going to identify voltages and currents with a subscript S and P, S being the secondary and P being the primary. Just want to remind you that when we're talking about transformers, the subscript P refers to primary and not peak. Previously we used the subscript P to indicate a peak value. Perhaps the most important parameter regarding transformers is the turns ratio. Turns ratio is simply the number of turns in the secondary divided by number of turns in the primary. It turns out that oftentimes manufacturers don't even give the turns ratio. What they instead do is give you the voltage rating for both the primary and secondary, and that is indirectly giving you the turns ratio because the secondary voltage is equal to the primary voltage multiplied by the turns ratio. By giving the voltages, it also gives you some additional information about the voltage capability of both windings, because when these transformers are constructed, you want to have the coils very, very close together. So you want to have very thin insulation. So as a result, the voltage rating of that insulation is very, very important. And by giving the voltage rating of both the primary and secondary, we are in turn giving the turns ratio. And also make sure that anybody that wants to utilize this won't make a mistake in terms of calculating, for example, the secondary voltage, and you'll just have it given in the ratings and it'll be much more clear that way. All right, so let's look at an example here. If we have 120 volts on the primary and a turns ratio of 20:1, in other words, 20 more turns on the primary compared with the secondary, then what is the secondary voltage? Well, all we do is multiply the primary by the turns ratio in order to get the secondary, and we would get 6 volts in this case. Just remember that the side of the transformer with more turns is always the side that has more voltage. Okay, so whichever side has more turns, that will have more voltage. When we have less voltage on the secondary than we do on the primary, that's referred to as a step-down transformer. On the other hand, if you have a transformer like this, 25 volts on the primary, 1 to 3 turns ratio, then we're going to get 3 times as much voltage on the secondary, and that would be referred to as a step-up. Excuse me. Okay, sorry about that. So this example is a step-up transformer. It has more voltage on the secondary than it does on the primary. The current relationship is exactly the inverse. The secondary current is the primary current divided by the turns ratio. And that assumes you have an ideal transformer. And when I say ideal, what that means is that there is no losses in the transformer. It's a perfect transformer with no losses. All right, so with an ideal transformer, the primary power and the secondary power are equal. Primary power is simply voltage times the current. Secondary, same thing, voltage times the current. So if we assume a 1 to 2 turns ratio and we have an ideal transformer, primary voltage is 35 volts, the load resistor is 700 ohms. We want to find secondary voltage and current and primary current. How are we going to do that? Well, first of all, we look at the voltage relationship. There's twice as many turns in the secondary, so there should be twice as much voltage. 2 times 35 gives us 70 volts in the secondary. And then we can simply use Ohm's law to get the secondary current. 70 volts divided by 700 ohms gives us 100 milliamps. 100 milliamps. And the secondary current will, along with the turns ratio, can give us the primary current. So we'll fill in our numbers. 100 is equal to primary divided by 2, or the primary is 200 milliamps. Notice this only works for an ideal transformer. We're going to have a little different procedure to find the primary current when we have a non-ideal transformer. All right, another example, 1 to 4 turns ratio. Secondary is 25 volts, primary is 100 milliamps. We want to know what RL is. So we can say the current relationship here is I secondary is 1/4 of 100, and that would give us 25 milliamps. 25 milliamps. And then the R of the secondary is simply the voltage divided by the current, which gives us 1 kilo ohm. 1 kilo ohm for this. And as I'm going through this, I tend to go rather quickly. Take a moment to pause the video periodically and do the calculation for yourself and make sure you know where all the numbers came from. All right, here's another ideal transformer, 2 to 1 turns ratio. Primary is 50 volts and the load resistor is 1K. We want to know what is the secondary voltage and current, what is the primary current, and what are both powers. So we look at the voltage first. We know the primary, and then the secondary would be 1/2 that, or 25 volts. Okay, and then we can use the Ohm's law to find the current. 25 volts divided by 1K resistor gives us 25 milliamps for the secondary current. Power in the secondary, we can do V squared over R. Again, your choice as to exactly how you do that. There's several power formulas, but you should get 625 milliwatts. 625 milliwatts. Okay, now that we have that 625 milliwatts, we can say the powers are equal between the primary and secondary. So the primary power is 625 milliwatts also, because this is an ideal transformer. And then primary current is the power divided by voltage, and that works out to 12.5 milliamps. 12.5 milliamps. Okay, take a look at this one. We have a 1 to 5 turns ratio, and we want to know what is the secondary voltage. And no, I guess I just want to point out here, secondary voltage will be 0 here because that's a DC source, and a transformer does not work for DC. Kind of a trick question. I just want to make sure you're paying attention there. Okay, any real transformer, actually physical transformer, is going to have some loss in it. It will not be perfect. Losses are from 3 primary sources. The resistance of the winding gives you I squared R loss. Hysteresis loss is a loss in the magnetic circuit. And eddy current loss, that's where you have currents induced in the core, and you get I squared R losses in the core because of this undesirable current. And all this leads to some efficiency factor. Efficiency is power out divided by power in, expressed as a percentage. And we abbreviate that with the Greek letter nu. That is the efficiency of the transformer. We mentioned eddy currents. One way to cut down on eddy currents, those currents in the core, is to make your core in thin slices and laminate it together with insulation between it. Here's an actual transformer, and you can see some of the thin slices there, and they're separated by a layer of varnish insulation. The layers of the core are stacked together here. I pried one off, and this is what they look like. And the coils of wire, of course, wind around here. And these are the coils of wire. So this would actually be on the face of the transformer like this. And there's actually a bolt that goes through here that I've removed in order to take apart this transformer to give you an idea how that laminated core works. All right, so in the real transformer, if you want to find the primary current, you first of all find the secondary voltage. Once you have that, you can find secondary power, and then use that efficiency formula to find the primary power. And once you have the primary power, you can find the primary current. So let's take a look at how to do that. If we have a 2-to-1 transformer, 2-to-1 turns ratio, primary voltage 100 volts, load resistance 1K, and now we have an efficiency of 95%. We want to know what is the secondary voltage and current, and what is the powers and the primary current. This is actually the same transformer we had earlier, but earlier we assumed it was an ideal. This time we have an efficiency associated with it. So the very first step is to find our voltage. 100 divided by 2 gives us 50 volts. Then we can do the current. 50 divided by 1K gives us 50 milliamps. And then we can do the power. Power in the secondary is 50 times 50 milliamps gives us 2.5 watts. Once we have the secondary power, we can use the efficiency formula to find the primary. 2.5 watts divided by the efficiency. Now you express the efficiency as a decimal. So 95% would be expressed as 0.95. So 2.5 divided by 0.95 gives you 2.63 watts. 2.63 watts. And put aside those values we had earlier, and now we can also find the primary power and from that primary current. So 2.63 watts we just found. Divide that by 100 in order to get the current. 100 is our voltage. Ohm's law here gives us 26.3 milliamps. 26.3 milliamps. All right, here's another example. 10 volts on the primary, 1K resistor on the secondary, 97% efficiency, and 1-to-2 turns ratio. So our little cookbook formula here to find the primary current, find the secondary voltage, secondary power, use the efficiency to find primary power, and then find your primary current. So the secondary voltage is twice the primary, or 20 volts, and the secondary power is V squared over R. 20 squared over 1K gives us 400 milliwatts. 400 milliwatts divided by efficiency of 0.97 gives us 412 milliwatts for the primary power. 412 milliwatts for primary power. And now we have primary power. We can find the primary current. Ohm's law, 412 milli divided by 10 gives us 41.2 milliamps. 41.2 milliamps. All right, and here's one more. We have 1 to 3.5 turns ratio, 20 volts on primary, 5K resistor, 95% efficient. We want to find the primary current. We can go through the same procedure. We find the secondary voltage, and that turns out to be 70 volts. Then we find the secondary power, 980 milliwatts, and the primary power is 980 divided by 0.95, or 1.03 watts. 1.03 watts. Okay, now that we have that power, we can use the power formula in order to get the current. 1.03 watts divided by 20 volts gives us the current, 51.6 milliamps. 51.6 milliamps. All right, so that was several examples of how to analyze current and power in a transformer. Hope you found it interesting, and stay tuned for more videos on Mark's Tech Talk.